this next talk is, I think the idea is to be a little bit more expository so that we get some of the CMSA locals who are not in this field to learn a little bit about it, to get some discussions going. And for that, we're happy to have Aram Harrow, who's a professor in physics at MIT, but with a very strong computational background and computer science, multi-information theory. We're happy to hear him tell us about monogamy, entanglement, and convex geometry.
Great, thank you. Thanks everyone for making it to the end of the day. Or if you just came here, then welcome. I think most of you who are here seem to have been at my tutorial. So I prepared this with some possibility that there wouldn't be, but so it'll be a mild overlap with what I said before, but I think mostly it will be, I will not spend time on that overlap, and mostly it'll be pretty new. What I want to talk about now are kind of the answer to David's last question. So I introduced this way of using SOS to address the separability problem, and then the question becomes, well, how large does K have to be, right? Everything really turns on that, at least if you're interested, maybe not everything. So I guess there's sort of the mathematical properties of it, where maybe you don't mind if K is very large in some cases. But if you want to do it, if you're interested in the computer science applications, then you really care about the efficiency of this algorithm. You care about how big K is. And if K is going to be bigger than n, and this thing is going to basically take exponential time, then you're not very interested in this as an algorithm. If K is going to grow like a constant or log n, then this becomes a compelling algorithm. And so I want to talk about cases where we can show that smaller K can work. And then my efforts to understand what's going on in those cases. And the partial success we've encountered along the way. So this, by the way, is my, whenever I have anything non-commutative, I like to have an excuse to use this comic. So yeah, this is, many things we do in life are non-commutative. And so quantum mechanics is just one of them. So I'm going to talk, what am I going to talk about? I'm going to talk about separable states and operator norms. How to approximate the set of separable states. Some results about doing this in the context of approximating more general operator norms. And then a lot of this is, you can think of it as optimizing polynomials over the unit sphere. But then I'll talk about a different case of optimizing over the probability simplex, which in some ways can be easier and may shed light on some of the things that go on for the sphere. So, okay, so this slide, actually not to single anyone out. Who was not at my tutorial? Anyone? A few people. So, if you were at my tutorial, there were still questions about it. So rho is a separable state if we can write it in this way, a probability distribution over product states. I can also think of it as a convex hull of density matrices. I don't know why this extra equal sign is there. And the weak membership problem is, you're promised that either rho is separable or far from separable, and you want to figure out which is the case. And the optimization problem is this thing called HSEP, the support function of the convex set. Given a matrix M, compute the maximum of trace M rho over the separable states. So those are the problems related to separable states that we will consider. Another class of problems that is hard, or can be hard, can be easy, can be hard, are to estimate operator norms. So let's suppose X is a map from space A to B. A and B will just be normed vector spaces. Okay, so they'll think of, and they'll always be finite dimensional, and they're equipped with some norm. And I will define the operator norm of X to be the largest ratio of the norm of the output divided by the norm of the input. And the catch is, because we're going from the space A to the space B, the output norm is measured, whatever the rules are for space B, and the input is the norm is defined according to the rules for space A. And so for these norms, we call this, the A to B norm, because it's the norm that you get when you're mapping from one, space A with this norm to space B with its different norm. So one example is if you take A and B both to be the L2 norm, then this gives you the largest singular value of the matrix A. So that just means, what is the largest Euclidean length of a vector that I can get? If I put in a vector of length 1, what is the largest Euclidean length I can get out? I multiply by a matrix. Another norm is L infinity to L1. So now you can think of A as a vector whose L infinity norm is 1, and I might as well restrict to the extreme point, so I can just assume the entries of A are plus or minus 1. And now I want to measure the 1 norm of the output. And because that's dual to the L infinity norm, I could also think about this as I take the matrix X, I just write it as a giant vector, and I take the biggest inner product I can with something in the form A tensor B, where A and B both have infinity norm at most 1. So if I can think of A and B as both plus minus 1 vectors, this is very close to the maps cut problem. I just want to choose A and B to make, you can think of this as a, you can think of X as a directed graph, and I'm coloring all of the sources plus or minus 1 and all of the sinks plus or minus 1. The start of every edge is colored by A, the destination of every edge is colored by B, and I want as many disagrees as possible, or as many agrees as possible. X determines the sign of X determines whether I want the two sides to agree or disagree. So this is a computationally hard problem. If I do L1 to L infinity, on the other hand, this is a very easy problem. It's just the largest entry of the matrix. So now, this is equivalent to taking the largest inner product between probability distributions A and B, and so I might as well just concentrate all of their weight on a single coordinate. For those familiar with quantum information, if I look at the Schatten 1 to Schatten 1 norm, this corresponds to how well two quantum channels can be distinguished. The S1 to SP norm comes up in other problems to measuring how noisy a quantum channel is. One norm that will come, the L2 to L4 norm. So you can think of this as it's like the 2 to 2 norm. You put in it's like that, and the input is still L2. You put in a vector with Euclidean length is 2, but you measure the output in terms of its 4 norm. And you can think of the 4 norm, I guess it comes up in that picture of the TV set. It's, I like to think of the 4 norm as, it's like the 2 norm, but it prefers to be more concentrated. And so the output is not just you're looking at the Euclidean length, but it favors, among vectors with the same Euclidean length, it favors ones that concentrated on the fewer entries. And this corresponds to some graph problem called small set expansion I'll talk about later. And finally, the S1 to S infinity norm turns out to be equivalent again to H-sep. So H-sep is equivalent to many problems, and one of them is the operator norm of mapping operators from Schatten norm 1, basically the Schatten norm 1 to Schatten infinity norm. And one way you can see this, I guess the way I wrote it is not the most clear. Let me write it out. If I take the S1 to S infinity norm, that's the maximum over alpha with S1 norm at most 1 of the S infinity norm of X. And if and this in turn is the maximum over beta with Schatten 1 norm at most 1 of trace of beta times X of alpha. So what I get is this is a maximum over alpha and beta, both it's like they're density matrices. Their Schatten norm is at most 1 of trace of beta times x of alpha. And so this is something which is linear in both alpha and beta, and I'm maximizing these over something that's like the set of density matrices, although I don't require they be positive semi-definite. Under some circumstances, the maximum is automatically achieved when they're positive. Easy, trivial, and quite hard. And there's an enormous amount that's computationally interesting that fits into this framework. And so what I want to talk about is the complexity of H-step and how it relates to operator norms and our attempts to solve all of these problems. So when you talk about the complexity of H-step, I want to talk about the complexity of approximating it. And it turns out that there are a lot of qualitatively different ways that you can approximate it. So, Boaz asked me at one point, which distance measure you're going to use. Which one you use really affects your complexity a lot. So, one way you might approximate it is you could say, well, I want to estimate H-step of M. And, it's a little bit like a quantum observable. It's like you can think of it as a Hermitian matrix. Let's say the eigenvalues are between -1 and 1. That sort of sets a natural scale of the problem. And so suppose I want to, that is the scale I'm going to use. So the eigenvalue between -1 and 1, I'd like to approximate it up to an additive error of some small constant, let's say 0.1. So this turns out to be a not super hard problem. It's a little bit harder than polynomial time. So it's shown to be as hard as something called planted clique, which I think if you know what it is, then good. If not, maybe it's not worth me getting into what I mean by that. Or I showed with Ashley Manginaro that it's almost as hard as solving a 3-set instance where the length is log squared of n. So remember, your matrix has dimension that's n squared by n squared. So if I could just solve it in polynomial time, that'd be polynomial in n. So if I had to compute the largest eigenvalue, I could do that in time polynomial n. This 3-sat, I only know how to solve that in time exponential in log squared n. So that's n to the log n. It's slightly harder than polynomial time. And that is the only hardness that we know for this level of approximation. So it's harder than polynomial time, but not dramatically so. On the other hand, if I want a multiplicative error, and here a quite large multiplicative error, let's say I'm willing to approximate it to within a large constant factor, let's say 100, then Boaz and I and many other people showed that if you could do that, you could solve this other problem called small set expansion, which I'll introduce later, but that's a problem where we don't really know how to solve this. We don't have anything like n to the log n for solving it. The only things we have for solving it look like 2 to the some power of n. And then suppose you want a very accurate approximation. These things are sort of constant additive error, constant multiplicative error. Suppose you want an error that's a 1 over polynomial fraction of the dimension. Now this is really as hard as 3-sat. And you can always. This problem can't be much harder than 3-step. Like if you want to solve H-step, someone could just tell you the solution. You could certainly verify a solution length order n. So you could always you could trivially solve this problem in time exponential in n just by enumerating overall possibilities. And this says if you want this level of precision, you can't really do much better than that exponential time approach. Okay? So the complexity of this problem varies dramatically based on the level of precision that you want for it. And how we measure the error. And in doing this, one thing that always bothers me is I don't know if we're measuring the error the right way. Like maybe if you came up with one more norm and you measure the error with respect to that norm, this would all make a lot more sense. So I introduced the diversity of operator norms and these wildly varying complexity results to point out that possibility that we just picked a few things that kind of made sense for some application. That does not mean that those are the right way to capture the complexity. This is just all we have to know so far. Yeah?
Do you get radically different algorithms depending on what measure?
Yes. I mean, kind of. This argument here is very easy.
Probably some space can capture what you do in all three cases.
I guess
It's just a huge overkill, maybe. In the
The
last
problem, the
case,
hardness results are different, right?
the hardness are very different.
They're different, but like these results are very easy. This one, element 2 to 4 norm, and this one is just really long, and it's I'm not sure it's the best proof of it. It's just the one that we happen to come up with. Like our paper is long, but then we build on a long paper by several other people, and it's it's not necessarily the best proof. Okay, so this is H step. Now let me talk about the 2 to 4 norm, and explain why this is interesting from a computer science point of view. So a lot of effort in computer science is trying to understand if I have a system of constraints, how, first people realize sometimes you can easily figure out if you can satisfy all the constraints or if you can't. And sometimes it's NP hard or NP complete to figure that out. And then, after people realize that, and it turns out most problems are NP complete, then, nevertheless, we'd still like to solve them, the attention turned towards approximation. So if something is NP complete, can we still get a good approximation to it? And then it turns out, approximating it, there may be algorithms might be able to approximate it up to some ratio, and to do better than that is NP complete. And there's a conjecture called the unique gains conjecture. If it's true, there's a single algorithm based on separograms that works for all constraint satisfaction problems that achieves a certain ratio, and doing any better than that ratio would be NP complete. So if that were true, it would dramatically simplify the landscape of optimization, of what is the best optimization ratio you can get, and how do you achieve it. We're just sort of simultaneously answer all of them. If it's not true, things might be a little bit more of a mess. What is the unique gains conjecture? One version of it that I think captures the main idea is, suppose I have a bunch of linear equations mod k. It could even be in two variables, so xi minus xj is equal to something mod k. It's easy to check whether these are all satisfiable or not. I can just do linear algebra in this finite field. Let's say k is prime. But suppose I want to distinguish the case that 99% of these equations are satisfiable, or no more than 1% of the equations are satisfiable. Now, this linear algebra-based approach does not work. We do not know a good algorithm for doing this. And this is called the unique gains problem. The unique gains conjecture is that this is NP hard. And it's unknown if that's true. And it's related to this problem called small set expansion, which is like the question of how good of an expander is a graph. So what I mean by that is we say the expansion of a set within a graph. Let's say I have a graph of vertices and edges, and I take a subset of the expansion of that subset is the fraction of edges that start in that set that leave that set. So think of the people in this room, pick a random person in the room, a random person that you know. What is the probability that that random person you know is in the room or outside the room? So if we were, like a cult that, we only knew each other, that fraction would be 1. If we were a bunch of strangers, that fraction would be 0. It'll be somewhere in between. And so what is the most disconnected set that you can find? That's called the expansion of the graph. And small set expansion says, I only want to restrict to subsets of the graph that are a small fraction. Let's say delta is like 1 over 1,000. So I want to restrict to sets with no more than n over 1,000 vertices, if there's n vertices altogether. And then I want to answer what should be a relatively easy problem. Can I find such a set where 99% of the edges leave the set, or at most 1% of the edges leave the set? Distinguish those two cases. Sorry, either there exists a set where 99% of the edges leave it, or for all sets, let me say it again. Either there exists a nearly disconnected set. There's a set where only 1% of the edges leave it, or for all subsets of that size, 99% of the edges leave it. Okay, so either there exists some cult somewhere that's disconnected, or everyone is super social and has tons of connections outside of that use. And it turns out this small set expansion problem, the games problem in computational difficulty, and it reduces to the 2 to 4 norm problem. So if you can compute the 2 to 4 norm on a graph, you can solve the small set expansion problem. Yeah?
When you say similar, you mean there's like a reduction, or?
There is a reduction, but it only works in one direction if the unique game instance is on a graph that is a good small set expansion. But Boaz can maybe tell you why that doesn't seem like a bad restriction.
Again?
You know, this equivalence here only works, right, for unique games that are on a graph that is a small set expander, but
Yeah.
people are not too bothered by that, it seems.
Yeah, I think it's kind of people, there are like several camps where morally it's the same as small set expansion or morally, but yeah, I'm of the camp that morally unique games and small set expansion are the same, but
Yeah. So, yeah, so, you know, to take this with a, you know, I think the way a lot of people feel like these two look closer than a lot of other things, so let's focus on other parts of the problem for now. But this is not settled on. And so, why is it true that if you can solve the 2 to 4 norm problem, you can solve small set expansion? The connection is a little bit like, if you're familiar with Cheeger's inequality, the connection between ordinary graph expansion and the 2 to 2 norm, you can relate the expansion of a graph to the second largest eigenvalue of the adjacency matrix. Right, so the largest eigenvalue will just be the stationary distribution. And the second largest eigenvalue will correspond to, if the graph roughly partitions into 2, then you could put, let's say, positive numbers on one side of the partition and negative numbers on the other side of the partition, and that will be an eigenvector that will have an eigenvalue that might be close to 1. That would correspond to the second largest eigenvalue. For small set expansion, you don't want to partition the graph in 2, you know, with 2 large sets. You want to have one really small set that's distinguished from the rest. And so you want to do a little bit like this eigenvalue game, but you want to bias the optimization towards vectors that are very concentrated on a small number of entries. And that's precisely what the 4 norm is good at doing. And so what you do is you say, look, let's say G is my normalized adjacency matrix. So G is, let's say the graph has constant degree. Take the adjacency matrix and divide by that degree. So this is like the random walk matrix of the graph. Take the projector onto the top eigenspace of that graph. So all the degrees of information that don't, the degrees of freedom that do not decay very rapidly when I do a random walk in the graph. If this were like a spatial, like if I was walking on the 2D grid, these would correspond to long wavelengths. And if these are always very spread out, then the 2 to 4 norm of this operator is going to be very small. And if there's one that's very concentrated, then the 2 to 4 norm will be large. And if there is one that's very concentrated, that means that there is a small set that doesn't expand very much. And conversely, if the 2 to 4 norm is very small, that means that all the small sets expand all the time. So by calculating the 2 to 4 norm, you can figure out the small set expansion properties of this graph. That's sort of hand-waved through the proof. The proof is pretty non-trivial. Boaz did it. I think some of our co-authors checked it. I'm very happy that I don't have to answer details of that if anyone has questions about it. But you know, at this point, I think you can appreciate that if you solve 2 to 4 norm, you can solve these interesting questions from complexity. So, good. So these are things we'd like to solve: HSAP and 2 to 4 norm. And so far, all I've done is I've told you why they're hard. Right? I said if you can solve HSAP, you can solve these other things. If you can solve 2 to 4 norm, you can solve unique games and blah blah blah. So, what about algorithms for it? So, the sum of squares algorithm I explained to you in kind of algebraic terms. Let me give you another picture of the sum of squares algorithm, and this is actually due to Pablo and Andrew Doherty and Spedalieri. But what's the first name? Frederic Spedalieri, from about 15-ish years ago. And their idea is to use the monogamy of entanglement property, which says the following. If I have classical correlations between A and B, there's nothing stopping those correlations also from being shared with another system C. But quantum correlations do not work this way. The more A and B are entangled, the less A and C can be entangled. And so if I have a state on systems A, B1 through Bk, and when I write A sub Bi, I mean the reduced state, when I just look at those systems, I trace out the remaining systems. If all of those reduced states are equal to the state I care about, rho AB, then if K is quite large, rho AB cannot be very entangled. So if rho AB were separable, there'd be no problem with having this property hold for an arbitrarily large K. But if rho AB is entangled, then I won't be able to take K, at some K, I won't be able to write it this way. And so as I increase K, these form a set of increasingly stringent tests of entanglement. When K is 1, there's no test at all, like anything will pass K equals 1. For K equals 2, some entangled states will be ruled out, but some will still, are what are called 2 extendable. I can write them as rho A, B1, B2 with this property. And if I increase K, the tests get tougher and tougher until if K is infinity, that corresponds to separable states. And now from an algorithmic point of view, the dimension of these things is growing exponentially with K. The runtime is n to the order of K. I do a semi-infinite program to search for this extension. So what I really care about is how quickly is this converging as a function of K. Just like what I said for sum of squares. And so so let me now define, just to remind you, let me define a slightly more general version of separable states. Before I said it was for 2 parties, this is for m parties. So if I have m systems, each n-dimensional, this is called sep nm. And the symmetric version, I just have m copies of the same state. Then there are a series of papers which are able to give and then this is the non-trivial part, but it's not too bad of a relaxation. The error goes like some constant times the log of the dimension divided by k, and then all of that square rooted. And so I said that often we have to take k bigger than n in order to get a reasonable bound. And this is not interesting algorithmically, that's exponential in n. Here, we only have to take k bigger than log n. And so it gives us an algorithm that runs in time n to the log n, which actually is kind of cute that it matches the hardness result I mentioned earlier. So that's the good news. The bad news is the first line of the theorem gives some caveats. So h-sep is something I can define for any m, but our algorithm, or this algorithm, works only for m of a specific form, and the m should look like a sum of ai tensor bi.
These absolute values or whatever norms are probably should not be there, right?
They should be there. Yeah, I know it looks like some PowerPoint font error. What do I mean by the absolute value of a matrix? Well, these are Hermitian matrices, so just take all their eigenvalues and replace them by their absolute values.
Okay.
And so what this corresponds to, you can think of this as Bob makes a measurement on his system, and he gets an outcome I, and he sends the answer to Alice, and then Alice makes a measure on her system based on that and decides whether the answer is, the overall thing is going to be yes or no. So in general, if m is an operator whose eigenvalues are between 0 and 1, you can think of it as a measurement whose outcomes are either 0. And this is a special case of that measurement. It's called a measurement you can implement with local operations and classical communication. So it's not the most general measurement you can do with a quantum system. It's one that can be done with Bob measuring his system and sending a classical message to Alice, and she measures her system. So a limited form of measurements. And this condition here on the B sub i's does not match our known hardness result. So it's frustrating, and that we have the same n to the log n. We have an n to the log n algorithm, which is very non-trivial. We have n to the log n hardness, which is very non-trivial. Each one took a lot of work to get, and they apply to different classes of measures. So I cannot say that n to the log n is the right answer, because this restriction we have in the algorithm does not appear in the hardness. On the other hand, just to really taunt us and to show us that these techniques do have the potential to have algorithms matching the hardness results, the same ideas apply to the multipartite case. So now, suppose there are m systems, and basically you measure each one of them separately. This is kind of like the Bell scenario. You have m parties, each one measures their system separately, sends a classical message to a referee who combines all the classical messages and decides what to do. This is what happens in Bell tests. Again, use something that's a lot like validity. I have to even define what k-extendability is in the multipartite setting, but kind of the multipartite version of k-extendability in these running times. And I guess the important thing to see is that we still have the log squared of n in the exponent. So this was, n to the log n. This is also like n to the log n. And then we also have this m squared of the exponent. And there's a paper by Chan and Drucker that has a hardness that matches this algorithm. So here, there's no, the conditions match up. They have a hardness result. We have an algorithm. They match, meaning that you cannot improve our algorithm or improve their hardness result without getting an algorithm for 3-SAT that seems too good to be true. So these techniques have the possibility of nailing down the complexity of it, but somehow they're not quite doing that for the two-party case.
Even for the multi-party, you still can ask this question whether, okay, even if you, for example, get an hardness that with those conditions, you can still ask the question,
Right.
If I drop these conditions, can I still get this
Of course.
algorithm?
That's true. That's a good point. Yeah. Yeah. It doesn't end the story for multipartite. So let me give you some sense of how do these things work. And the clue is that these measurements are a special form of measure. They're ones where Bob measures his system and sends a message to Alice. And so we can imagine doing the same process for the extension. So remember, we now have one Alice and k Bobs in this extendable state. So they can all of the Bobs can measure their systems, and they get answers B1, B2 through B sub k. They send them all to Alice. And let me think. And then basically what I want, it's a little bit tricky. I don't want Alice to make her measurement based on any particular one of those Bobs. Instead, what I want to do is I want to look at Alice's quantum state and argue that it doesn't have very much entropy once you condition on these measurement outcomes from the Bobs. That Alice's state is nearly determined by these Bobs. And so the way the proof works is illustrated by another Far Side cartoon. I don't know if you can read this. It's damned if you do, damned if you don't. And you have to choose one door or the other one. So the way to think about this is if they measure their state, then there's kind of a few possibilities for the probability distribution. Either A and B1 is nearly independent, in which case we're already done. So remember, we're trying to get k extendable states to approximate separable states. And so if A and B1 are nearly product, then we have a nearly product distribution, and this looks separable. Or if they're correlated, then that means that if I condition on B1, then A and B2 will have less mutual information. And so then I can do the same thing again. I can say now, condition on B1, are A and B2 nearly independent? If they are, I'm done. If not, condition on B2, and each time the mutual information keeps on dropping. And the reason why mutual information is so helpful here is that the mutual information can be at most log n. If these systems have dimension n, the mutual information is an entropic quantity. It scales like the log of the dimension. And so that's why I'm able to have k fighting against log n instead of fighting against n. Because I only need to do log n rounds of this before the mutual information becomes negligible. Any questions about this?
We don't have to consider the mutual information between B's, like B.
No, because we're ultimately interested. The question is, do I care about mutual information between B's? So go back to this k extendable realization here. So remember, each a b sub I matches my original marginal. And so they all have the same state. And so if I can argue that any one of them is nearly separable, and so if a times n is nearly separable, then I'm done. And separable, remember, means it's a convex combination of product states. And so conditioning on B1 through B6, that just means there's some classical variable, which are the measurement outcomes of B1 through B6. And once I condition on that, A and B7 are left in the nearly product states. That means that once I average over those measurement outcomes B1 through B6, then this is left in a separable state. So I guess some questions already at this stage are, we have this runtime of x log squared n, and I mentioned it appears in both the algorithm and the hardness. The arguments that lead to this x log squared n are totally different. Actually, even the epsilon dependence is the same. The arguments that lead to this are totally different. I don't know if it's just a coincidence or if this truly is the complexity. And the types of M, in one case it's one LOCC, this means one-way local operations and classical communication. In the other case, M, I said M is like a fully general measurement. You can restrict it slightly to be something called a separable measurement, but it's still quite a bit more general than what the algorithm applies to. And then the other thing is, can we improve these algorithms to get what we need for small set expansion? We were hoping at some point to use these things to get a good algorithm, maybe n to the log n for small set expansion. But they fall short of that. Just for small set expansion, you need multiplicative error, and we achieve this weaker form of error. So these algorithms, I would say, are promising and very non-trivial, but they fall short in many ways of the things we'd like to solve. In trying to understand them, we came up with a completely different algorithm that also yields n to the log n, that in some ways is a lot simpler. At least the analysis, I think both the analysis and the algorithm are simpler. And has nothing to do with sum of squares. Or maybe it does, we don't know. So again, let's let M of B of this form. Now we're going to have Alice send a message to Bob. We saw that sum of squares hierarchies get this runtime. One way you can view H step, if you want to maximize over alpha and beta, you can view it in this way. Let S be the set of probability distributions that can be achieved by Alice's measurement. And so you can think of this as you have the state alpha and beta. Alice measures the state with her measurement with outcomes A sub I and sends the measurement result to Bob, who measures it with B sub I and decides. And this probability distribution P is the distribution that Alice gets over her choice of measurements. So the probability of outcome P sub outcome I is P sub I, just trace of alpha times P sub I. Okay? So she sends message I to Bob with that probability, and then he measures B sub I. So then, the ultimate value is going to be, I think I only wrote it down here. So you can think of it like this. Alpha is a density matrix for Alice, and then alpha gets mapped to a probability distribution P that lies in delta M. So delta M is probability distributions over M objects. So suppose that Alice's measurement has M choices, then this will be a distribution over at most M things. And then that distribution is going to get mapped into Bob's measurement. So effectively what Bob's measurement is the sum over I of P sub I, that's the probability, times B sub I, that's what Bob does. This is effectively Bob's measurement. It's something in the unit ball of S infinity. In other words, its operator norm is at most 1. And this can be used to define the norm, which I'm calling the B norm. So the B norm of a vector x is you just multiply x sub I by B sub I, and you take the 2 to 2 norm of that. And so H sep, you can think of it as the maximum over probabilities P that are in this set of things you can get from alpha of the B norm of P. And this set S are just all the possible, I've just written it out, all the possible probabilities that you can get from this process of measurement by NLS. Okay, so I just rephrased HSAP in this for this special case of these kind of measurements. I've rephrased it. Now that you've rephrased it this way, it admits a really simple algorithm, and the idea is to just take an epsilon net over the space of probability. So I've just kind of moved everything up in the slide a little bit to make room. So what I'm going to do now is these blue dots are going to be a net of regularly spaced points in the set of probability distributions. Specifically, they're going to be k-sparse probability distributions. In other words, all of the probabilities are integer multiples of 1 over k. And so there's going to be, so that's sort of a way of, you can approximate any probability distribution that way, up to perhaps some error. And you can prove that for any probability distribution p, you can get a good approximation by k-sparse probabilities, and the approximation error looks like our usual friend, square root of log n over k. So k just needs to be on the order of log n in order to get a good approximation. And the proof of this is really just like a matrix generalization of the Chernoff bound. It's due to Augustin and Winter, who basically show that if you take a bunch of random matrices and average them together, they approach their expectation value kind of the same way that scalars do. So the algorithm now is very simple. We just enumerate over all of the k-sparse probabilities, and there are not that many of them. The number just grows exponentially with k. It's going to be m to the order k. And we just check whether there's a nearby point p that could have given rise to q. In other words, we want this purple set. We look at over all these little blue dots, and we figure out if they're close to the purple set or not. If they're not, we ignore them. And if they are, we evaluate the b norm of that point. We just pick the best one. Okay? So it's a very simple algorithm. You just have to enumerate over this epsilon net. Gives you essentially the same approximation guarantee. So what is the performance? We have to take k to be like log n over epsilon squared. Now, the base of the exponent is m, the number of measurement outcomes. But you can always take m to be polynomial in n. You can basically just, if there's many more of them, you can just take a random subset and you'll give a good approximation. And so the runtime is again exponential in log squared n over epsilon squared. So we get the same runtime, it's a very different algorithm. Any questions? So I'm running a little low on time. I will say you can generalize this, give any norm spaces A and B. Let me just skip this, but you can kind of generalize this to any norm spaces, and then the performance is going to depend on properties of those norm spaces. Those properties are called the type 2 constant. Anyway, you get essentially the same algorithm there. So this generalized a little bit beyond just this Schatten infinity norm to general norm spaces. We can apply this to the S1 to SP, L2 to LP, low rank measurements. There are a few cases, I don't want to give the impression these epsilon nets give just exactly the same results as SOS. They give you some slightly better things in other cases. Since it's late in the day, I don't want to spend too much time on this, but this generalizes in a slightly different direction. Question?
Sorry, this is under an OCC, or you're saying for other classes?
It's all under LOCC. Well, originally it's one LOCC. Maybe I'll say, what does it look like if A and B are general norm spaces? Then the one LCC, I guess this gives some insight, so I should talk about this. The one LCC restriction corresponds to my map from A to B has to go through L1. You can think of LCC now as, I take a density matrix, I map it to a distribution, and I map that to a measurement. So the distributions live in L1, the L1 unit ball. And so if I replace A and B with general norm spaces, but my map goes via L1, I get the same kind of algorithm. And that's kind of the crucial, geometric feature of this, is that it's going via L1. And so you can think of it as, I want to estimate the A to B norm, but the approximation error I get is proportional to the A to L1 to B norm. And this is like how well can I approximate my map by one that factorizes through there? And there's one other little way in which this is worse than the SOS ones, which is for the sum of squares-based algorithms, it was enough just to know the matrix M. Whereas here I need to be, or X I guess here I'm calling it. Here I need to be given the decomposition. These net-based algorithms depend on the decomposition. You have to be given it, it's not easy to find. But the other ones you only need to know the overall matrix. So they're not exactly equivalent. On the other hand, for some cases like low-rank matrices, they can do better. If I were to estimate L2 to LP for higher P, they do better. So in some cases they do better as well. Slightly better. They have slightly different, they're not exactly the same, but for the original problem of H-step, they give the same performance. And it's late in the day, I'm a little running over time, so I don't want to spend too long on this, but in trying to understand this, we realized that there were a ton of examples where epsilon nets and sum of squares give you essentially the same answer. So there's maximizing a quadratic function over the simplex, and there's approximate Nash equilibria. There's something called free games. So here you have two provers, and you ask them both questions, but your questions are uncorrelated. There's unique games, and this, I think the same B is Boas for both of them. Right? You did both versions of the unique games thing, right?
And it's free games.
Unique games.
Unique games, yes.
That was, yeah. Small set expansion, also Boas in both of them. I guess same paper there. And H-step, I just told you about that. So maybe I'll
Although I think the result I'll talk about tomorrow is with H-step with general measurements is the one case where we don't know if a net algorithm.
Oh, that's right. Yeah. I'm going to get to that. Right, that's one of the open problems. Yeah. So I guess to shed a little light on this, I'll talk about the polynomial. The simplex. So delta n, I'm defining to be the probability simplex over n things. So n real non-negative numbers that add up to 1. And I want to now maximize, let's say, a degree d polynomial over this. And over the variables are p1 through pn, so it's a probability distribution. So these are not polynomials, these are just real numbers. This is an NP-complete maximization problem, even though the simplex is not too hard. You can solve this, you can figure out the largest clique in the graph. And there are two natural approximation algorithms for it you can consider. One of them is you enumerate over all k-sparse probabilities and just try out your polynomial on each one of them and see which one gives the best answer. That's called the net-based approach. Or there's the sum of squares hierarchy. So the net-based approach, of course, will give you an upper bound. We're trying to maximize, right? So it will give you a lower bound. It won't achieve the true max, it'll give you a lower bound. The hierarchy will give you an upper bound. And basically here, I've written out a little polynomial equation that you're trying to find. But it's very simple. You just want to find lambda such that lambda times this thing here should be always 1 for probabilities. Lambda times this thing minus your polynomial times perhaps some power of this thing, which should always be 1. You want this thing to always have non-negative coefficients. If so, that will correspond to a very simple kind of sum of squares proof that f of p is at most lambda. So that will give you an upper bound on the maximum. And it turns out each one gives you very similar error performance. And the error is going to go down like 1 over k in each case. And Paolo, I think, showed this equivalence. And I think I'll skip what this is. And basically, the explanation that was in Pablo's paper is that if you look at the sum of squares proof, so it corresponds to just writing f of, coming up with this equation, lambda times this minus f of p. You use the fact that your normalization constraint shows equal to this, and then if all of these coefficients are non-negative, then this will be greater than or equal to 0. So you're trying to find a decomposition of this form. The dual of this is equivalent to enumerating over a certain epsilon net. So in this particular case, the sum of squares algorithm really can be exactly mapped to an epsilon net algorithm. And the reason I think this is possible is that it's not really a semi-definite program. It's really just a linear program. And so there's a polytope, and the vertices of those polytope can be mapped one-to-one into a corresponding epsilon net. So really kind of a special case where here there's a really natural correspondence between them. And in the simplex, so for the probability simplex, we understand that. For general problems, we simply don't. So I think, we can also find the Nash equilibria. I will skip that. And maybe I'll conclude with some open questions, which are, I'll start with this bottom one. Can we explain these coincidences between sum of squares and epsilon nets? I'm hoping that will shed more light on the whole thing. We understand it only for the case of the simplex, and a little bit for, not in many other cases. We'd also like to get a tighter hardness result for each step. I've talked about that already. We'd like to ultimately solve things like the unique games problem and small set expansion. There's a possibility of these results either giving better algorithms or better hardness results. And we've made some progress there, but we haven't achieved as strong results as we'd like. There's a paper that Boaz will talk about tomorrow, which is one of the few cases where sum of squares can give you a non-trivial approximation guarantee for each step, but we do not know a corresponding epsilon net-based approach to it. And in general, I think this points you to a large mix of optimization problems where they're all somewhere between P and NP. We have some techniques for them, some hardness results, but there are many, many more things that we don't understand. And I think even understanding why our algorithms work is something we also could use some help in understanding. So hopefully this will lead some of you to solve some of these. Thank you for all your attention today. And by the way, here's the papers that these are based on. Yeah.
Is there a net-based algorithm for like the two local Hamiltonian problem, like the version of the non-commutative sum of squares? Can that be? Is there a net-based algorithm that achieves the same thing for the low levels of that?
No. Or I don't know. So one place where SOS works, let's do a simpler one, which is Goemans-Williamson.
Right.
We do not have a net-based algorithm for Goemans-Williamson. So what the nets correspond to, I don't mean to imply that they recreate everything that sum of squares does, but for a large class of problems where sum of squares gives you a non-trivial approximation guarantee, often with this kind of runtime, then nets seem to do the same thing.
But the examples you gave are somehow like all examples with just two parties. I don't know if is that a distinction that matters here? Like Goemans-Williamson is on a graph with n vertices.
You can think of two parties as like degree 2, and Goemans-Williamson is a degree 2 function over vectors of plus or minus 1s. And the simplex thing, that goes up to arbitrary degree D. So, I don't know if I would agree that it's two parties. If you go back to this list of equivalences, so they're not. You could say that there's certain commonalities among them, and I would agree with that, but they're not all reducible one to another. Each one you kind of have to do fresh. So
I guess the first one is most similar to Goemans-Williamson.
Yeah, first one is kind of right. I like that. It's L1 instead of L infinity, but otherwise it's like Goemans-Williamson. So I think I agree with your larger point that there is a large class of what SDPs and even sum of squares does that does not look like this, and it would be nice, it'd be nice if we could more clearly draw the line between. I think there is some kind of regularity here where the same proof idea is being used in many places, and maybe that proof idea is captured by epsilon nets. And so I think that is what that is what is missing here. We have some hints that is the case, but not yet a complete theory.
Is there a reason to always use uniformly distributed nets over your simplex?
Yeah, so well, can you give an idea of what else you would use?
Maybe you'd like something that's more concentrated here at the boundary. Maybe you expect things to be.
Well, these are kind of close to the boundaries, right? Because these are k-sparse. So these are, all the probabilities are multiples of 1 over k. And think of k as quite a bit smaller than n. And so the entropy of these distributions is very low. It's at most log k, whereas, maybe a typical probability would have entropy closer to log n. So, in a sense, these are kind of close to the boundaries in some sense. I do like the idea that maybe we could be using a more intelligent net. I don't have an idea of which one to look at, but it's true that, I hope that came across actually in this talk. There have been a number of algorithmic achievements, but there's a certain lack of creativity in all the algorithms I've presented. So there's definitely room for more creativity in nets. I just don't know what, hopefully someone else will come up with one.
Any other questions? Now let's thank Aram again.